Good afternoon, everybody. Thank you for hanging through to the penultimate talk of the penultimate session of the conference. Uh, I want to take this opportunity to significantly thank Cynthia Rudin, who was the person who sort of put most of this together. And now it is my pleasure and privilege to introduce Matthew Phillips from LifeOmic, who will be speaking about biomedical image understanding and EHRs at LifeOmic, harnessing the power of the cloud.
All right, okay, sounds like you guys should be able to hear me. I too like to thank the organizers for bringing me back in this case. Nice to see the event growing. Okay, so here's what I'll be doing today. Just a very small bit about me, then talk about LifeOmic, who we are, not exactly a household name yet, so that'll need some introduction. And then two significant projects, significant for me, that I've been working on there. One involves clinical notes, which are part of the spectrum of documentation that goes into an EHR. So it's great that I'm following David Page, who has set this up so wonderfully, so you guys all know what EHR means. And the second bigger project is about biomedical image segmentation. And then at the end, I'll talk about some future work that's just getting off the ground now, which involving multimodal AI. So yeah, very quickly, I started out as a neuroscientist, actually, moved to Duke to do a postdoc, got into industry, and then found out that realized machine learning was really where I belonged all along, and came to LifeOmic about 9 months ago, where I'm kind of a principal machine learning researcher there, which means only machine learning researcher there. But the projects I'm going to describe are things that I've largely created, at least the ML component of them. It's a marvelous, wonderful opportunity. So, LifeOmic. LifeOmic is not, ML is not the sort of raison d'etre, the bread and butter of ML. Fundamentally, what we're about is precision health, precision wellness, tools to support that, infrastructure in the cloud, something called the Precision Health Cloud I'll be talking about and describing, because that's where sort of the magic happens for a lot of the stuff I do. We also have a security project, a product, which is very interesting, but I won't be talking about that today. So it's mostly engineers, and it's also a mobile platform, a mobile product, which is great. I could spend a whole talk just on the mobile product. But the machine learning actually exists more currently to support this storage, data storage and infrastructure product that serves the healthcare system. So it's called Precision Health Cloud, PHC. And you can see how it has fundamentally, or it's intended to have an integrative role. We do a lot with precision health, so this is a buzzword you hear a lot, and that has kind of two possible senses, and we're heavily invested in both. One is your genome, genomics, integrating that into sort of better personalized treatment for you, because we know what your genes say about you, and we can use that to come up with better diagnoses and things like that. And also personalized health in terms of tracking your particular history, your measurements, your weight, your labs, all of that stuff over time, your personal sort of health record over time, tracking that and using that more effectively. Because as David sort of indicated, data are siloed all over the place. You need a PhD just in, seems like you could get a PhD just in health records. The system is so complex. So yeah, there's a great app. No time to really talk about that. We also have a lot of academic partnerships. So we integrate with research labs, especially at IU, which is where we're headquartered, and researchers, physicians. One of these projects, actually the first one, comes from a partnership we have with a physician in Indiana who works on multiple myeloma cases. Here's our big stack, plus more stuff that IU has contributed. That's part of a big project we have with IU. The Scion is LifeOmic. And so I guess what's kind of interesting here is, which you can look here, is FHIR, this acronym, FHIR. That's a new standard for describing healthcare data. And it looks like it's a pretty smart attempt to deal with just this enormous complexity of documentation and record keeping. So it's a format. It's basically JSON. So we do FHIR ingestion, and you'll hear talk about a PDF a fax to FHIR, that's converting a fax document into FHIR, which is highly structured and machine readable. And you can see our ML AI box. And the other thing is, yeah, you see VCFs. Those are variant call files. That's individual genomic data. So that's something I'll maybe talk a little bit about. We have some data with that, and we can analyze that on our platform. So this is, it's this big thing that exists basically on Amazon, and it's, HIPAA and high trust certified and all that. Okay, and then, yeah, we have these services. Interestingly, this slide, which I didn't make, is sort of cloud agnostic, but it's all AWS right now. And we put things in Docker containers, and then we run them as task services. And so we can actually, on your data, we can create algorithms and analytics that run on them, and then run on that data on the cloud, and then we visualize it for you. Okay, so much for LifeOmic and its products. First project is cleaning up clinical notes. So this is nothing short of fascinating, I would say, from kind of a sociological perspective. But in the year 2019, okay, not 1989, but 2019, we have somebody who, communication, ER communication is done with a fax machine. Okay, we have someone who described, who had a lengthy history as a heart patient, how to transfer his records from one clinic to another, a nurse had to manually photocopy them and then hand him the paper stack. And this was in March, right? I mean, it's like time warp. But this is how it is. And so, a lot of the times a fax might be clean and easily readable. But first of all, it's an image. And so there's a huge need here to digitize this and kind of bring this into the system into the modern era. And there's a huge backlog. So even if everything went purely digital tomorrow, there'd still be years and years of these documents literally sitting in boxes that need to be understood. So there's this huge push to develop systems which can take these documents, read them in, and understand them, and then turn them into the kind of digital record that you can analyze and make machine readable. And OCR, optical character recognition, that term will describe sort of the entire process here. Okay, so our solution is going to basically take this fax document, which we'll get as an image file or a PDF, denoise it, send it to a product that Amazon has called Textract, which does what it sounds like. It extracts text and to some degree the structure, so it can understand a table when that table is rendered clearly. This ontology service is kind of just an in-house name. That'll be for looking up medical terms, which can then be searched in one of our visualizers. So the workflow, and this is, by the way, the top row here is how it is. Actually, which one of these is the? Okay, yeah, there we go. The bottom row is how we want it to be. Once is a significant incremental improvement that we could achieve with this service. And the key thing here is the middle. The medical abstractor, that's a human being who takes these fax documents that have been scanned in, looks them over, highlights the medical terms, pulls this stuff out and types it into this system called REDCap. And we want to, we don't want to replace her or him. We want to take the boring part away out of her or his job so that they can do more interesting things. And this task, which eminently should be done by a computer in this day and age, have it actually be done by a computer, right? So I mentioned our solution. So then the part that's interesting for us that I'm going to be talking about is this part, which is basically a computer vision problem. And here's what you get. Now, these are real clinical EHRs, which I've cropped so that they're completely, there's no PII here. But this is a real record. This is what they'll actually be dealing with. And what's interesting is, I'm calling this dither. That's kind of abuse of the term. But for this kind of speckle pattern, and this came, somebody had the right, their heart was in the right place, right? The original document had sort of gray shading, presumably. Okay, and that makes it more readable when you have the original. Well, you send that through a fax machine. And by the way, this is why it's so great to deal with real world data, right? I couldn't have imagined these kinds of things, but in the real world, this is common, okay? So these tables, where they've made some rows shaded for readability in the original, now create a real problem when they've been sent through a fax machine. So I'm making up all these little names, right? There aren't official names for fax noise. feel free to use them. So I'm calling this cell residue. It's really kind of the same thing as you just saw. And then sometimes it's this, weird black background. That will fool text recognition for sure. Then this is an interesting one. Okay, you see that faint pattern there? That's the document that was on the other side of the piece of paper when it was faxed, right? And so the fax light is the thin, low-quality paper, I guess. The fax light shines through and picks this up, calling that ghosting. That'll break TextRect. And then this is really tough speckle, right? And you can see somehow some residue from a table for some, I don't know where it comes from, but this is what it looks like. And now documented noise. First of all, boring, right? I want people to think that. I'm the only guy at LifeOmic who can work on this. So this problem has not attracted a lot of research attention, which is, like I say, an opportunity that I'm very, very happy to seize because it's as interesting a problem as anything in 2D computer vision, I would think. And there's just precious little on it. I mean, there's image denoising work. There's a toy Kaggle competition on it, about which I'll have more to say in a little bit. There's one paper now, one group that's finally come up with an end-to-end system. They only show results on this Kaggle datasets, though, so I don't really know where that's at. But like I said, couldn't find anything off the shelf for this. And notably, I expect there's closed solutions, proprietary solutions for this, but on all the things I just showed you, AWS TextRect fails. So state-of-the-art isn't perfect yet, even the worst of those was human readable. Okay, so how do we solve it? And we partially solve it. I'd say we've made significant progress. We don't get it all. So we just treat this as a segmentation task. Okay, we're going to use an attention unit. Actually, at this point, for what I'm showing you, there's lots of tweaks to the architecture plan, but there aren't any in there. And we tile up the document, break it up into high-resolution tile, so we get the full resolution, even interpolating by expanding it to sort of enhance the curves and so forth, and apply that network to it. And we get some wins here when we do this. So the model completely, now you're seeing results, right? The model completely understands dither. It's never seen, these are test set documents. It just eliminates that dither completely. TextRect now can understand this document completely, whereas before it actually couldn't. It does declare partial victory. So, before, nothing. Now, okay, it's been cleaned up. Again, the low spatial frequency backgrounds, it understands and can eliminate almost completely. This is obviously pretty garbled, but just enough that you could now Control F, or an automated system, right, that's getting hundreds of these documents, could search for these terms, maybe find them, maybe reroute this document and save some human decision, right? So maybe a partial victory here. Ghosting, nailed it. Okay, gone. Now it's the actual text which we care about does not look that pretty. Doesn't look any better than it did here, but the ghosting itself is gone. And linear speckle, we did well up here, you could say, but it's seeing characters in the noise, especially down here. So can't really declare a win here. I don't think this helped with TextRect. So how about that Kaggle data set I mentioned? Turns out to be a pretty toy data set, but nonetheless, since it's never seen that data set before, it's an interesting test. It literally came to me, I think, literally Wednesday night, and it hits it pretty well. Pardon this is just tiling error. I was just lazy, basically, but the Kaggle data set has stuff like on the left, and as you can see, we get that noise out pretty effectively. A nice coffee stain. Again, never seen data, anything like this. And it hits it, nails it, gets everything, pretty much. It also, well, except the dots on eyes, but otherwise, basically gets it. So the model is largely successful. Some kinds of noise it can handle, some kinds it can't, and look out for hopefully a paper on this and the product itself to drop sometime soon. Okay, so what about the power of the cloud? Okay, it's there. I'm running short on time, so it's on the cloud too. We have a task service for it. All right, biomedical image segmentation. So this is with retinal fundus images, and if you've had any contact with if you're in touch with any of the competitions, you've probably seen 10 different Kaggle competition announcements based on retinal fundus images. They're really important for a lot of reasons. There's lots of things you can diagnose with these images. They're actually also cheap and easy to acquire. You can go into a clinic and get these images, maybe even with a handheld device. You could do it. But 3 tasks I'm going to talk about. Find the optic disc, that's what this is. Find the fovea, and find atrophy, okay? And segment it. So another segmentation task. And correspondingly, we'll also bring out the attention UNet. There's 2 ideas that I've developed for this research. It's unpublished yet, but so far, but working it up. And one is called output recycling, which is where you take the output of the network and you feed it back in as an input, as a sort of a prior. You exploit the fact that the output space, the output of a segmentation network, has the same metric structure as the input, right? That's not usually the case with, say, standard classification, but it is with segmentation, and you can actually exploit that. Variants of that have been done before, but not quite the way I do it. And then the other idea is CoordConv, which is not my idea, but I think it's an idea that has been undersold and is actually far more interesting than people realize. So output recycling. Here is a UNet, okay? And I can't get into details about how this works any more than what I'm showing here. But fundus image in, segmentation out. At the top, the task is find the atrophy. At the bottom, the task is find the optic disc. Okay? Now, you get these masks, and then you add channels. Okay? You add input channels to this network. Okay? That's the key idea. If you understand that, you understand what I've done here. And now, with these coming in as essentially extra input channels, you feed all of that into this network, and you come up with what is visibly, and this is a real case actually, visibly better segmentation. There's the optic disc, and the atrophy usually encircles the optic disc here, so you see the clear sort of relief. All right, CoordConv, on the other hand, is similar in that it adds input channels, but here you're adding gradients, okay? And what these do is they tell the neural network where you are in the image. I'm not going to have maybe enough time to fully do this justice, but a convolution can learn this. And the key insight here is that, unlike the sorts of things I covered in the actual CoordConv paper, in biomedical images, there are geographic regularities. Okay, the heart is usually in the center. The lungs are usually symmetric and off to the sides. In a retinal fundus image, the optic disc is usually off to the side, the fovea is in the center. When you have regularities like that and you use CoordConv, a convolutional neural network can learn those and leverage those regularities. And then when you get to volumetric images, where you're forced to take very small patches of things, this is a potentially very powerful idea. So we will see what progress I've been able to make with that. So first of all, with CoordConv, I already mentioned the gradients, and you saw small versions. Here's what they look like in the actual retinal fundus case. X, Y, and then a radial gradient. And again, these will go in as input channels, okay, just like R, G, and B. Okay, here are just some illustrative segmentation results. They're not beautiful, but they show the model now with both CoordConv and output recycling, functions competently, let's say. So optic disc, that's an easy task, and the model finds it, right? Fovea location, I actually treated that as a segmentation task as well. These look like they're off-center. They're actually not. This is a fundamentally correct identification of the fovea. Here is 2 atrophied regions, and it's a little, it's not a dice score of 1, but it basically gets it in either case. And dice scores, in fact, range from about 0.6 to 0.9, kind of depending on task. Some more illustrative results. I won't go into these in any detail, except for one interesting one, which is, I guess an experience somebody else shared, where this optic disc down here actually wasn't annotated. It found an optic disc that the human annotators couldn't find. So for optic disc detection, it performs beautifully. And then does well on atrophy protection and very well on fovea detection. So I'll keep trucking along. Yeah, and so now, okay, so how about these, evaluation with respect to these 2 ideas I described specifically, starting with output recycling, right? So that's where you you have actually multiple incarnations of a unit, right? You train one to produce images to just segment the optic disc, segment the atrophied regions, and then the follow-on unit takes these as inputs and comes up with a better prediction using them as priors. And critically, there's no sort of cheating involved. These networks are obviously they're trained on training data, but this system with this recycling does not require on an official label. It relies on a segmentation, but that just comes from a trained model. So you can apply this to the test data. There's no secret sort of using the actual label in this. And what we see is pretty significant gains for output recycling. So what you're looking at, OD for optic disc, A for atrophy, F for fovea. These are multi-class tasks, okay? And the numbers are dice scores. So we're classifying two things at once. That's what the plus sign means. And when you just segment these things without output recycling, these are the numbers you get. When you do this multi-class segmentation, but now the network is getting these inputs, these priors, performance jumps up. Okay, so output recycling leads to non-negligible improvement in segmentation. How about this CoordConv? Okay, so the most difficult task was fovea detection. And interestingly, that's the only one where it helped. But retinal fundus, these are relatively small biomedical images and relatively simple. So, I'm happy to get a win just in this task. And what I found out is that the patch size means, so pardon me. The images, they're simple compared to, say, volumes. Anybody who works with biomedical images knows that, the fun really starts when you get to 3D volumes, right? But these are still actually very large images. I mean, the original scale is like, they're 1,000 by 1,000 pixels or something. So a patch size of 25% literally means, I just took a 1/16 of it and fed it into the network, okay? And then tried to segment that, and it was trained on patches like that. And so without CoordConv, if you fed the network, tried to train the network on patches like that, it just couldn't learn. It just could not figure out how to find a fovea when it's just getting patches from different places on the image. And the more, the smaller the patch, the greater the improvement that CoordConv enabled. So CoordConv, we started a little late, I guess, but I'm nearing the end anyway. So no, this is working out time-wise. So the point is hopefully clear that CoordConv to this more difficult fovea detection task made very significant contributions, especially when the patch size was small. And maybe that's not so directly relevant for retinal fundus images, but you think about tasks where the images are really quite large and you have no choice but to deal with them patch-wise, or you have to either deal with patches or shrink and subsample and potentially lose important detail. CoordConv is potentially could be very important. And precisely one such case is, keep me mentioning volume segmentation. This is this hasn't really even started in earnest yet, but here's a unit just on treating these as 2D images. Again, a unit, doing great. But these are two slices of a volume, right? So now we're talking about, 100, now there's a Z depth of, say, 100, 200 slices, 200 pixels. And just all I have with this at the moment is just what these gradients look like. And so you can see them X, Y, and then now here's the Z gradient, right? Giving you depth. And so this would all go into the network, or does all go into the network, and tells you where, not just where things are within the patch, but then where the patch is within the entire volume. And when you consider just how small, right? This is now the label, this is the pancreas, I think. Just how small, this cursive dimensionality, right? Just how small the labeled object can be relative to the entire size of the image. It's tiny, right? It's bad enough with 2D images when you're segmenting, an optic disc in a huge retinal fundus, but when you're segmenting an organ within the entire thorax, right? Now you're dividing through, even further. So that kind of segues into now the future work, where I've finally, after much struggle, gotten this data from the government, a sort of small data set from the VA yeah, the Veterans Administration healthcare system. And it's potentially a very, very valuable data set. Data is hard to get in general, is kind of the moral here. As part of a federal initiative to improve healthcare and modernize it and bring digital tools to it and get companies like LifeOmic to help develop these tools. It's got broad, lots of interesting data from relatively few subjects. But among others, it's got this volumetric data. So the stuff I told you about with CoordConv, what I'm going to do is apply it directly to this data, and stay tuned for that. I'm looking forward to getting this project off the ground. Here's just an example of how we've got it represented in PHC. So that's it for the talk. Two very, very important collaborators along different dimensions, Ananth, our engineer, and Beiju, the deal maker. And then finally some community work. I organize a meetup, which is not like other meetups in that we really go after the sort of in-depth technical discussions. It's great. We have some great speakers lined up, including somebody who's going to be talking to us about Bayesian optimization in 2 weeks, an expert in that, Chris Fusting from DivePlane. It's co-organized with a guy who does NLP, just got his PhD from USC, Mari Cortland, who's been giving great presentations on NLP. And with that, thank you.
Thank you so much. We have time for a question or two. Well, if I might ask a question. Oh, wait, I'm sorry. Yes, sorry.
Okay. So, yeah, I mean, we're really working to more and more stuff is getting transferred over to FHIR. Okay. And so we kind of build increasingly around the assumption that we're going to be seeing data in FHIR format. Otherwise, I mean, we work with kind of whoever we're working with. I mean, I still have a lot to learn about documentation systems and things like that. But we get the structured data and we have tools for analyzing it and ingesting it. Couldn't really do it justice, but we get it thrown up onto our visualizing tools pretty effectively, so you can search it. But we don't have any kind of, I guess either I don't know or we don't have any kind of standard system beyond a general push to make everything sort of work with FHIR. That would be the closest thing I could say to that is sort of FHIR based. But we work with every data set and every provider, we don't exclude anybody for sure.
Yeah, the reason I'm asking this question is I work with EHR a little bit, and one of the challenges that in current EHR practice is the interoperability. So seems like each EHR vendor has their own kind of proprietary kind of standards or things. So how do you solve this kind of thing? Like do you have a lot of challenge like in cleaning the data and make all the things standardized?
Yeah, so this is why I'm so glad I thanked Ananth Iyer by name, our engineer. Those are the guys, he and other engineers we have are the people who understand this stuff better than I do. So, I hear RedCap, Epic, Cerner.
Yeah,
these
Epic, yes.
Okay, these are names I hear. I have not been that close to that kind of stuff, but I'm sure. There's challenges involved. For sure, and we handle them. How? I guess I just don't know, frankly. Anything special or interesting, I couldn't tell you because I'm just not that close to the front end. Yeah.
Thank you very much.
Okay.